Hello everyone and welcome to another PAT Problems video. My name's Helena and I'm the Access and Outreach Manager for the Department of Materials at the University of Oxford, and today we're going to be taking a look at another question from the 2014 PAT paper. So the question we're going to look at today is the other long question on the paper, which is question 18. And because this is a long question, it's going to take a little bit longer to go through. Again, we're going to split this video up into two. There's going to be two parts to this particular question. So let's look at the first couple of parts of this question to get us started. So this question is all about optics, and we're thinking about total internal reflection, optical fibers, and refraction. Okay. So in this question, we're also told that we can assume that the refractive index of glass is larger than that of water, and the refractive index of water is larger than that of air. So we're going to be thinking about these different sorts of interfaces. So just to write that, we're using the letter N as our refractive index. Refractive index of glass is larger than N of water, which is larger than N of air. And you might remember that the refractive index of air is usually 1. Okay, so that's a good thing to try and remember, and that might prove useful in a later part in this question. Okay, so to get things going, we're being asked to think about a couple of definitions to set the scene for the question. So part A is asking us to explain what is meant by the phrases total internal reflection and the critical angle. And we can explain in words, and we can also use a diagram to explain these as well. So I'm going to do both. And to save you just watching me write out sentences, which isn't very useful to anybody, I've already written out the definitions here that I would use. So let's go through these now. So thinking about the critical angle first, if you imagine we have a light ray traveling from a higher refractive index material to a lower refractive index material, such as going from glass to air, for example, the critical angle is the incident angle at which light travelling across this boundary refracts to travel along the boundary itself. So we don't have any reflection, we don't have any refraction through the boundary, the light ray travels across the boundary. And I'll show that in a diagram in a second. And you might find that usually we call this critical angle theta C or theta crit, using theta to represent the angles here. So I'm just going to write that here. That's how I'm going to represent my critical angles throughout the rest of this question. Okay, so bearing that in mind, let's look at total internal reflection, sometimes abbreviated to TIR, which is how I usually abbreviate it. So this occurs when, again, we've got light incident upon a lower refractive index material at an incident angle which is greater than the critical angle, such that we have no light refracted through the boundary. It's all reflected back the way it came. So it's all reflected internally. And this allows light to propagate through a material without any losses. So that's going to come in useful when we're thinking about our optical fibers in the next few parts. So if we were to draw this as a diagram, which it is useful to do to visualize, let's have a look at sort of 3 different scenarios that we can have. So I'm going to set up a little diagram like this, where we've got our 2 refractive indices, N1 and N2. And remember, we're told it's going from higher to lower, so our N1 is greater than N2 here. Now, if we have an incident angle, theta I, which is less than the critical angle, we're going to have refraction across the boundary. So it's going to bend slightly, but we are going to have some refraction through the material there. We might also have a little bit of reflection. That sometimes happens, but we're going to get some light propagating across the boundary. Now, if we have the limiting case, where our incident angle here, theta I, is equal to theta C, this is where we have our light ray propagating across the boundary here. So this is what that looks like. So we've got our incident light ray, and it refracts so that it travels across the boundary. We don't get any transmission or any reflection. Now, the third case that we can consider is if our incident angle, theta I, is greater than the critical angle. And that is how we defined total internal reflection. So what happens here is we get reflection rather than any refraction. So we don't get any light transmitted across the boundary. It's all reflected back into that same layer. Okay, so that's how we define these in words. That's also how we explain these using our diagrams here. And like I say, this is the example which gives us our total internal reflection. Okay, so we've thought about the science. Now let's look at the second part of the question here. Okay, so now we're being asked to derive an equation relating the critical angle and the refractive indices of two materials, N1 and N2, where N2 is smaller than N1. So that's the case that we've had here. And we're being asked for this particular scenario here, where we've got the critical angle. So let's draw this scenario again a little bit bigger. So we have our boundary. I'm going to just put some marks here to show the boundary there, and draw our normal line. Again, we've got N1 and N2, where N1 is greater than N2. Again, sort of going from like glass to air or something like that. We've got our incident light ray, incident at an angle theta I, and we're being asked to consider the critical angle, which means that our light ray is going to propagate across the boundary, which means here that our theta R is 90 degrees. So that's going to come in useful. So we have the case where our theta I is equal to theta C. We've got that theta R is equal to 90 degrees. Now let's think about an equation to relate all these things together. So the first thing that comes to mind is Snell's law. Now this relates refractive indices to angles of incidence and reflection or refraction. So let's write this. It's N1 sine theta I is equal to N2 sine theta R. All right. So our theta I is theta C, our critical angle. Sine of theta R is actually sine of 90 degrees, which hopefully you remember is equal to 1. So that leaves us with an equation N1 sine theta C is equal to N2, or sine theta C is equal to N2 over N1. So that is the equation that we're being asked to find. And it's fine to leave it in terms of sine of the angle rather than writing the inverse operator on the other side. It's fine to leave it like this. Okay, so that's the equation we're being asked to find. That's going to come in handy for the rest of the question, which we are going to look at in the next video.